Hello, general chemistry students. This is Dr. Ryan Hayes coming at you live, kind of, as I make this recording. Today we're going to learn about scaling up or down, redox chemical reactions, picking the best oxidizing or reducing agent, and a little bit about electrochemical cell notation. Those three things. I have a question on the screen. Can you figure out which species is the best reducing agent? Go ahead and pause the video and see if you can figure that out. Remember, lots going into these things. Got to know the oxidation state of everything, who's oxidizing, who's reducing. We're assuming that you know these things coming into this video. If not, time to go back and review some of those things. All right. The reducing agent is the chemical species that gets oxidized. It's the one losing electrons. It's the one becoming more positive in charge. Chloride goes from a -1 to a 0 charge in the chlorine as it goes through the chemical reaction. All right, don't forget you probably have homework in OWL to be working on. And now on to our topic of scaling chemical reactions. Now the redox chemical reactions are unique to us. They're special, they're becoming more important. We're learning about scaling them in this video because there might be something unusual that you need to learn about that. It's a little bit different. So in the past, we've learned about scaling up chemical reactions. Let's say you had a chemical reaction like, say, the oxidation of iron, also called rusting. This has a huge free energy to this. Now, if you were to scale this chemical reaction and double it, you would end up doubling the free energy associated with that, or any fraction thereof. If you did it in half, then you would cut the free energy in half. And when it came to equilibrium constants, we could calculate it for this particular chemical reaction, and it's huge, astronomically huge. This is a very product-favored chemical reaction, and if we were to double that so that we would want to figure out the equilibrium constant for the second chemical reaction, what would we do? We would end up squaring it. All right, now the question for our electrochemical knowledge here is what would happen if we had a chemical reaction like the oxidation of zinc as it loses electrons? What if you had to figure out the voltage for twice that chemical reaction? What would the potential be? And it's interesting to think about. Would I double it like the free energy? Would I square it? Or maybe something unusual is happening. I'm going to half or square root it. Maybe does it stay the same? What do you think? All right, the answer is stay the same. What? But all the other ones change. Why didn't this change? Well, we need to consider the units of redox, volts. Volts is defined as joules per coulomb. Joule, of course, is the energy of a chemical reaction, or kilojoules, doesn't matter, but it's energy, joules, divided by coulombs. That's a little bit newer for us. What is a coulomb? Well, 96,485 coulombs is 1 mole of electron. And if I had 2 moles, I would have twice as many coulombs. All right. So if we're scaling the chemical reaction, let's say we're doubling it, well, we'd get twice as much energy out of it, and we would get twice the amount of electrons coming out of that. So whatever the coulombs associated with that chemical reaction, we would double it. So if you double the joules divided by double the coulombs, you end up back to the original joules per coulomb. And for the stunning conclusion, nothing happens. Scaling a redox reaction doesn't change the voltage at all. If you want to do half, it's still the same. Double it, still the same. The number doesn't matter. All right, all that for nothing, it seems like. All right, now on to our next topic. How do you pick the best oxidizing or reducing agent? The winner gets a mug. No, they don't. But you might be able to get a green check mark in your OWL homework, and more importantly, be able to make important decisions about who's going to react with who. So we're going to learn about some tips and tricks here to figuring out who is the best reducing agent, especially given a smaller set of chemical reactions to pick from. All right, so here is our set right here. We're going to have, we've got 3 reduction reactions in front of us, and we're going to ask these questions. Who's the strongest and weakest oxidizing and reducing agents? And let's see if you can figure this out. All right, so there are some rules to this, but let's get started and see if we can think about it. Who's the strongest oxidizing agent? Ooh, this would be great if you could click in and figure this out. Well, what do you think? All right, well, the answer is iodine, I2. Why is that? How do we figure this out? Well, remember, the oxidizing agent is the one that's being reduced, and we want to add in our knowledge of being reduced with the highest positive voltage. Well, when I look at my potential reactants that can be reduced here, that's iodine, nickel 2 plus, and manganese 2 plus. Out of those three, only iodine is the one that is reduced with a positive voltage, thus the strongest oxidizing agent. All right, next question. Who's the weakest oxidizing agent? Oh, we need some music, huh? Well, did you pick manganese 2 plus? Or maybe you tried to pick something else. You see, when we're being asked the question about oxidizing agent, there's only three that you can pick from: iodine, nickel 2 plus, and manganese 2 plus. The other chemical species are not involved here at this point. So out of the ones that we can pick, the weakest is manganese 2 plus, because it's the negative, it has a negative voltage, negative 1.170 volts associated with that. All right, now though, we're going to switch the question and ask about reducing agents. Okay, we're switching to reducing agents. Those are the ones that are being oxidized. That means we've got to reverse all the chemical reactions and think about those. And in this case, I minus is the worst one. It's now going to have a negative voltage, a negative oxidation voltage, because when you reverse the reaction, you reverse the sign. So it's the weakest reducing agent. Our reducing agents are going to be picked from the chemicals that are now on the, as we see them in front of our eyes, they're the products. But if we're thinking about oxidation, we're going to think about the reverse reactions. So who's the strongest reducing agent? Well, then that's going to be the one at the bottom right here, the manganese solid. When we think about the reverse reaction, we think about having the highest positive voltage. Now we're going to look at these last two questions here. Can I use manganese 2 plus to oxidize I minus to I2? Now, instead of just talking it through, I want to try to lead you through my thought process in figuring this out. So I'm going to jump to another slide here and see if we can figure out how we can think through these different parts. All right, so I've got to think about, if I want to know who's going to oxidize or reduce who, I've got to think about the set of reactions that I can reduce with and the set that I'm going to oxidize, lose electrons. Okay, so notice I have flipped everything. I've done the reverse. So I have it in my mind, but now on the screen, I have the list of reduction potentials and the oxidation potentials. I've switched the sign. I've even switched the nomenclature, so it's EOX. So now I'm going to think about how can I partner these two things based on the reaction here and the question that I have to give me an overall positive voltage. So I can only pick from the reactants now when I'm thinking about these things. So that's I2 nickel and Mn manganese 2 plus for my species that can be reduced. My only options for chemical species that can be oxidized are the bottom ones there: iodide, nickel solid, manganese solid. Okay, so how do I decide? I'm going to partner half reactions and put them together so that an oxidation and a reduction reaction together give me a positive E cell. Now, when I'm dealing with this question, can manganese oxidize I minus to I2? I go and think about the reduction potential for manganese, because if it's going to oxidize someone else, it itself is going to be reduced. All right. Now I look at the I minus to I2 oxidation reaction, which was the reverse of what was actually shown. Then I'm going to think about adding those two potentials together, and I end up taking the negative 1.170 volts plus the negative 0.535 volts of the reversed reaction down there, the half reaction for the oxidation, and together I get a negative 1.705 volts. This reaction will not take place between these two. That was like the worst combination one should use for this. Not going to work. All right, I have another question in there. The other question was, which species can be oxidized by nickel 2 plus? Who oxidized by nickel 2 plus? Well, that means nickel 2 plus is going to be reduced. So, okay, I'm going to leave nickel 2 plus in the way that it's written in the top there, and I'm going to get its negative 0.25 volts. I need to partner this with an oxidation voltage that's going to be greater than that and create an overall positive cell voltage, okay? So I picked that top one, and which one of the bottom ones can I pick? When I take a negative 0.250 and I'm going to add, which one should I add? Negative 0.535, positive 0.25, or positive 1.170? Which one of those three numbers is going to give me the highest overall cell voltage? Well, hopefully you picked, well, we can only pick one of those three, but hopefully you picked the 1.170. That last chemical reaction there, when I partner that one with the nickel plus 2, I will find that when manganese solid, I'm going to take that now and put it with nickel 2 plus, and I can get a positive spontaneous chemical reaction to occur. So that's how I think through those two chemical reactions that are taking place there. All right. So that the question then, who can be oxidized? Then I think, can this happen? No, if we determine that that cannot happen. Which species can be oxidized by nickel 2 plus? The manganese metal. So the reverse here of this reaction. So I have to have my imagination going and think about the reverse reactions. So that's how I go through those. It's important to understand that when we think about who can be the reducing agents, it's really just those things that can be oxidized. And who cannot be reducing agents, you can't just grab anything you see. There's reasons why you can't use things like iodine solid and nickel 2 plus and manganese as reducing agents, because that means they're going to have to be oxidized. That means they're going to become more positive. And you're going to put a positive charge on an electronegative I2, that's not going to really happen. Nickel 2 plus is already very positive, and so making it a 3 plus and manganese a 3 plus, that's going to be much harder to do. So can't say maybe it cannot be done, but the voltages are going to be very negative associated with any kind of oxidation with those. So there's realms of possibility here that we have, and not possible, that we have to think about. And this is the learning that a general chemistry student has to go through, is what's possible and what's not. Last thing we're going to talk about is electrochemical cell notation. You may have seen in some videos that there's this little line, funny line things. They'll write chemicals and put lines between them and then a double line. Well, what is that? How does that work? Well, we use that to describe redox reactions, electrochemical cells that produce energy or not. We like to list the anode on the left-hand side. Cathodes are listed on the right-hand side, put a double line in between them. If we're dealing with aqueous species, we like to put those concentrations, we like to specify them, and you'll often see them listed with the concentrations. Here's a simple example. Manganese solid with a manganese aqueous, whoop, no concentration given there. But we put a line in between when these two species are switching phases, going from solid to aqueous. If they're both aqueous, we just put a comma in there, and I think I have an example of that. Double bar, that represents the salt bridge. And then on the other side, we see the reduction that's taking place. Anode, oxidation on the left, cathode on the right. All right. So there's not much information in our textbook on it. It just says standard line notation, the anode is listed first, cathode is listed last, double line separating the two. By convention, electrodes are at the end with all the solutes and gases towards the middle. Well, electrodes mean sometimes you got to use like platinum or something that's not really a part of the chemical reaction. We're going to put those at the end. Let me see if I can give you a few more examples here. Let's say you're dealing with a situation where you've got 1 molar solutions and gases are at 1 atmosphere. And let's say that's all you're dealing with here is aqueous and gaseous materials. Well, who's oxidizing, who's reducing? Well, I'm going to assume you already know how to do that. I'm just going to give you the oxidation half reaction and the reduction half reaction, and fairly balanced for the most part here, except for the number of electrons. Okay, notice in both of these, there's no solid involved. But in order for electricity to flow, you got to have a solid. So we can insert one hypothetically, typically platinum or a carbon. These are very inert electrons. They don't react. So we're going to use that here in this full-on electrochemical cell notation, line notation for this electrochemical reaction. So I'm going to throw platinum in here. Yeah, it's hypothetical. It's expensive, I know, but hey, it's only letters on a electronic board here. And notice how I've written the chemical species now, and I put the molarity in, and I separate them by commas because they're all aqueous. No phase changes there other than from the electrodes at the end to the aqueous species in the middle. So hopefully that gives you some more experience dealing and writing with the oxidation reduction reactions, how you might see them. Now there's more videos that people have highlighted. I think do a pretty good job. So I've got a few of them here. I'll post my slides in our classroom learning management system, and you'll be able to see them there. So there's a few good things there. Well, we've learned a lot in this video. How to scale chemical reactions, what does that do to the voltage, how to pick the best oxidizing and reducing agents, and a little bit about electrochemical cell notation. I want to go find my words, and hopefully you'll find some interesting information here as you watch this video. Thanks for joining me, and we'll see you next time.